All right, today as we continue with our chapter, we are going to be talking about counting principles. So counting principles, a lot of this is going to have to do with probability, some of which you may have learned previously in Algebra 2 or in stats. So we're going to go over a couple of basic concepts when it comes to counting principles. So we're going to start by talking about a couple of terms. First is the sample space. The sample space is the list of all possible outcomes of an event. Okay, the list of all possible outcomes of an event. Now, when we talk about sample space, there are two ways in which we can talk about sample space depending on the problem. The first is when we talk about sample space with replacement. So this is when the sample space remains constant throughout the scenario, regardless of the number of events that occur. So in other words, just because one of the items in the sample space has occurred, it can still happen again. So it has been replaced with replacement. Without replacement is the second type. This is when the sample space changes with each event. So, for example, it might be something like pulling out a blue marble from a bag. You don't replace it. What happens for the next scenario, the next event? Well, the sample space has now changed because you're now missing that blue marble. All right, another important item when we're talking about counting and probability is using the word and versus the word or. So in general, remember that and means multiply. So what is the probability that this event and this event happens? You would multiply those probabilities. Or generally means add. So what's the probability that this will happen or this will happen? Well, you add those probabilities together. Okay, and then the fundamental counting principle. If x is the number of ways a first event can occur, and y is the number of ways a second event can occur, and this is really just applying the and versus or concept here. So the number of ways the first or the second event can occur is going to be x plus y. See, it's or, and you add. And the number of ways the first and the second can occur is going to be x times y. So, and means multiply. So if you can remember those two things, that will actually take you pretty far in terms of what we're going to be doing today. Okay, so let's take a look at some simple examples. A local cafe has a lunch special menu that lists 4 salads and 5 sandwiches. For $5, you can have any salad or sandwich for lunch. How many options do you have? Okay, so in this particular case, it does say 4 salads and 5 sandwiches, but what are you looking for? It says you can have any salad or sandwich. How many options do you have? Well, if it's an or, salad or a sandwich, you just add them together. So 4 salads or one of 5 sandwiches. So altogether, 9 options. Okay, that's a pretty straightforward example, but just so you can see how we're using that and or in terms of using it in adding or multiplying to find how many options we might have when this is a counting principle. How do we count out how many different options there are, how many possibilities there are? Let's take a look at example 2. A restaurant offers a meal deal where for $9.99, a customer can order 1 appetizer from a choice of 3 appetizers, 1 meal from a choice of 7 dinners, and 1 dessert from a choice of 5 desserts. How many different possible meals can be created? Okay, so for this deal, you have 3 parts, right? You pick an appetizer, and you pick a dinner, and you pick a dessert. So because we're saying and, we'll just write this out, appetizer and dinner and dessert. Now we want to know how many different possible meals can you create? Well, how many options are there for appetizers? There are 3. For dinners, 7. And for desserts, 5. So 3 times 7 times 5. Those are all the different ways that you can come up with a different meal. And so this comes out to be 105. So there are 105 different meals that can be created from the 3 appetizers, 7 dinners, and 5 desserts. All right, let's take a look at example 3. How many different 7-digit phone numbers are possible within each area code? Local phone numbers cannot begin with 0 or 1. Okay, so 7-digit phone numbers, so we're not worrying about area codes or anything like that. So it's going to be 1, 2, 3, 4, 5, 6, 7. And now we just need to know, okay, for each of these spots, each of these blanks, how many possibilities are there? Well, each digit, right, how many different digits are there? From 0 all the way to 9, that's 10 digits that are possible. Now, it does say that local phone numbers cannot begin with 0 or 1. So for that first slot there, we can only have 2, 3, 4, 5, 6, 7, 8, and 9. That's 8 possibilities. For the rest, though, they can be any digit from 0 to 9, so that's 10 possibilities for the other 6 slots. All right, so now all we have to do is multiply those, and we can come up with, let's see how many zeros that is. Looks like 6 zeros, so that would be 8 million phone numbers. Okay, so that's just the 7-digit phone number, not including the area codes. You can come up with 8 million phone numbers. Okay, the next thing we're going to talk about are permutations and combinations. So a permutation is an arrangement of objects such that the order matters. Now there are a number of different places where this could be the case, but where order matters, it could be how many ways are there that you can line something up, okay? How many ways are there of putting some pictures up on the wall? How many ways are there for people to win a horse race, something like that? But any indication where the order matters is going to be a permutation. Okay, so we're going to look at an example and see how we can come up with the number, how do we count, right? We're talking about counting principles. How do we count up how many different ways there are of arranging objects? Okay, so there are 8 runners in a race, and how many different orders can they cross the finish line? Okay, so there are 8 of them. That means there are 8 places that need to be filled in, right? So here are the 8 places. Now, how many different possibilities are there for that first slot, for someone to be in first place? There are 8 runners, so any of those 8 could come in first. Now, after someone has already taken first place, how many possibilities are there for second place? Well, we're down 1 runner, so now there are only 7 possibilities for the next. Okay, the first and second places are now filled. How many runners are left that could fill in the next space? That'd be 6. And you continue this on and on and on. So this looks like what? It looks like 8 factorial, right? All right, so this comes out to be 40,320. And the number of ways to arrange n objects in n spots is n factorial, right? We had 8 runners, we had 8 spots to fill, and to find the number of ways to arrange those runners, it was 8 factorial. So you'll use this when order matters and when you use the entire set of elements. What do I mean by that? I mean, this example could have said, in how many different ways can they come in first, second, and third place? That'd be a different problem because it doesn't matter to us who came in 4th, 5th, 6th, 7th, and 8th. So in that particular case, you wouldn't use 8 factorial. So this is only when you're using the entire set of elements. There are 8 runners, there are 8 places to fill, so you find the number of ways to arrange them is 8 factorial. Okay, so now let's talk about, okay, well, what if it was, how many ways can the runners place first, second, and third? Again, like I mentioned before, that means that we don't care about who comes in fourth, fifth, etc., etc. Just how many ways are there that the runners can place first, second, and third. Now, do we expect this to be more or less than example 4? Well, in example 4, we cared about all the other places. If we don't care about all the other places, then we should have fewer ways for the runners to place first, second, and third than there are to place them from first all the way to 8th place. So let's apply the same concept here, but we're only interested in the first 3 slots. So in first place, there are 8 possibilities. After that first spot is taken, then we only have 7 runners left who can take second place. And after that, we only have 6 runners left who can take third place. And that's it. It's just 8 times 7 times 6, which is 336 ways, compared to our 40,320 ways of them coming in first through 8th place. Now, for something like this, for this example, wasn't too bad to write in the slots, but we want to be able to come up with a formula that we can use that will make this simpler. So that way, if you say you had 100 runners and you wanted to know how many ways can the runners place first through 50th place, you really don't want to be doing out 100 times 99 times 9 all the way to the 50th one, right? We need some sort of formula to help us simplify this calculation. And so that's what we have here on the next slide. So in general, the formula for finding a permutation of n elements taken r at a time, so it's a permutation, so order matters. There are n elements, and you take r at a time. So r could be equal to n, doesn't have to be though. As long as it's smaller than or equal to n, you can use this formula. So here it is. So normally the way that we read this is n permute r, NPR, okay, n permute r. And then on the top we have n factorial, and on the bottom we have n minus r, in parentheses, factorial. So you use this when order matters, and you will not be using the entire set of elements. Now, if r is equal to n, what ends up happening? You end up with n minus n, which is 0 in the denominator, and then 0 factorial is equal to 1, which means n permute r is, or n permute n, is just equal to n factorial. So you can absolutely use it when you are taking all the elements. It's just a little bit longer. It's a little bit easier if you just remember that if you are using the entire set of elements, it's just n factorial, but it still works in this formula. Okay, now there is one slight adjustment when you have what we call distinguishable permutations. Okay, so distinguishable permutations require a slight adjustment when elements of a set repeat themselves. So when we talk about distinguishable permutations, we're talking about probably not a race of some sort. Maybe you're talking about lining up a set of books on a bookshelf and you have 2 of the same book, and those 2 books are not distinguishable. So then when you're trying to come up with, well, how many different ways are there of ordering the books on the bookshelf? Now you have to take out the fact that 2 of those books you can't distinguish between. So therefore, if you swapped those 2 books wherever they are, those orderings are really the same because they're not distinguishable. So how do you adjust for that when you are only concerned with distinguishable permutations? So let's take a look at this example. How many different arrangements are there for the letters in the word bookkeeper? So even just before we get into this, if you were to take the way it's arranged right now, let's say you took the 2 Ks and you swapped the 2 Ks. It looks exactly the same, but technically we've come up with a different arrangement. right? It's the same letter. It looks exactly the same. It's indistinguishable. But if we were to use what we were using before, there's going to be an issue because, well, if we use what we did before, we're taking into account all those indistinguishable permutations. So in order for us to do this, we'll start off by first taking all of the objects. So we're arranging all of these letters, right? So the number of distinguishable permutations of n objects is going to be n factorial. But if there are any items in the sample space, in this case letters, that are not distinguishable, so for example the two O's, the two K's, the three E's, if there are anything that repeats that you can't distinguish between, we are going to divide those out, because really what we're doing is we're saying, well, if you take the two O's and you just swap them, it looks exactly the same. It's not distinguishable. So we want to divide out those extra arrangements that look exactly the same. Okay, so bookkeeper has 10 letters, and we know that the E repeats 3 times, the K repeats twice, O repeats twice. So on the top, you write down the number of distinguishable permutations and divide it by any repeats. So in this case, the E repeats 3 times. So we're going to take out 3 factorial. K repeats twice, so take out 2 factorial, and same with the O. Okay, so doing this out and dividing by 3 factorial, 2 factorial, 2 factorial, this comes out to be 151,200 arrangements. Okay, so that's permutations. Permutations where order does matter. Now combinations is an arrangement of objects such that order does not matter. Now, you actually already saw this formula when we were talking about binomial expansions, the binomial theorem. We saw this, you may have also seen it before in stats or in algebra 2. So this formula here, n choose r, is equal to n factorial divided by n minus r, parentheses factorial, and r factorial. Okay, when does order not matter? Order doesn't matter if, for example, it might be something like in a deck of cards, you draw a hand, right? The order of that might not matter because you just have whatever it is, 6 cards in your hand. You still have those 6 cards. That's a case where order doesn't matter. It might be coming up with a group of, let's say, picking a group of students out of a class. The order, which doesn't matter, but they're all going to participate in something, right? So those are examples of where order does not matter. So we'll do 2 examples with this, but hopefully you're fairly used to this formula by now. All right, example 7. A standard poker hand consists of 5 cards dealt from a deck of 52 cards. How many different poker hands are possible? Okay, so you have how many cards can you choose from? 52 altogether. How many do you want? You want 5. So out of 52, you choose 5. So we'll go ahead and apply the formula. So that's 52 factorial over 52 minus 5 in parentheses factorial times 5 factorial. Now again, try to simplify it as much as you can. So in the denominator there we have 52 minus 5, which is 47 factorial. So on the top, we would probably want to only go to 47 factorial. That way now we can cancel out 47 factorial from the numerator and the denominator. And then now we can simplify what we have left. So 52 times 51 times 50 times 49 times 48, which is 311,875,200. On the bottom, 5 factorial is 120. Divide those, and we get 2,598,960 hands. The last example we have says a class consists of 8 boys and 12 girls. If a committee of 5 people is to be chosen to represent the class, how many different committees are possible if the committee must have 2 boys and 3 girls. Okay, so let's think about what we need at the end. We need 2 boys and 3 girls. So remember, and multiply, right? So now we have to come up with, well, how many different ways are there for us to choose 2 boys, and how many different ways are there for us to choose 3 girls? Well, in this class there are 8 boys, so out of the 8, we choose 2 of them. The order doesn't matter, right? It doesn't matter if we chose this guy first and that guy second. It's just 2 boys are chosen. We don't care the order, they're going to be on the committee. Okay, so out of the 8, we choose 2. We'll do the same thing with the 3 girls. There are 12 girls altogether. So how many different ways are there of choosing 3 girls? Well, 12 choose 3. All right, so now let's go ahead and use the formulas to simplify this. So we have 8 factorial divided by 8 minus 2 factorial, 2 factorial, times 12 factorial over 12 minus 3 in parentheses factorial, 3 factorial. We'll do the same thing, only go out as far as we need to. It looks like in the denominator we have 6 factorial for the first fraction and 9 factorial for the second one. So we'll only go up to 6 factorial in the numerator and then 9 factorial in the second numerator. Right, so 8 times 7 times 6 factorial, and then 12 times 11 times 10 times 9 factorial, and that way we can cancel out the 6 factorials and the 9 factorials. All right, and then that leaves us with 8 times 7 divided by 2, which is 28, and then 12 times 11 times 10 divided by 3 factorial, which is 6, and that is 220. And then we can go ahead and multiply those two together, and we get 6,160 committees. So if you are randomly choosing from these 8 boys and 12 girls, how many different committees can you come up with? You can come up with 6,160 committees.